So the first step towards understanding how an insulator deposited by sputtering might be different from an evaporative metal process is to recognize the directional characteristics and ion bombardment effects. They're not the same for both types of processes. And as you can see from basically the early structure that was fabricated, we have a condition that looks very stable, and under an evaporative metal deposit would work quite fine. However, in the case of a sputter deposition, where you have a lot more ion bombardment, you can see that simply, 1500 angstrom deposits of silicon dioxide cause a significant amount of deflection of the beam, or the top side resist on the bilayer structure. So initially we had to sort of go about quantifying what the interactive variables were, which seemed more or less sensitive at different deposition thickness points, and effectively looking at the outputs from multiple runs to understand how interactive these were and how to optimize them as a combination. And so, as you can see here, the approach was to effectively categorize the structures depending upon the amount of deflection of the beam, and whether it was uniformly deflected. In the case of something with significant deflection or irregularity in the symmetry of the structure, it was just considered an unstable outright reject. If it was bowed significantly, it was considered a reject. If there was a very, very small deflection and it didn't appear that it was having any effects on the uniformity of the deposit, we would consider something like that borderline accept. But for the most part, what we were really looking for was undetectable change in the symmetry or flatness, essentially, of the top layer resist relative to the substrate. And for the deposition ranges that we initially looked at, which was about 1,000 to 2,500 angstroms, looking at 6 micron to 9 micron lines and spacings, we were able to get pretty stable structures with a range of about 2 to 3.6 micron top resist thicknesses, with undercut ranges of 1.8 to 2.5 microns. The pedestal is a critical element in the stability of the structure, and our findings indicated that down to just below about 1 micron, we were able to get high stability geometry.